So our last method of integration we will be learning is called integration by parts. And it's basically just a formula. I'm not even really sure where the formula comes from, but I know it works.
Let's find Google.
Maybe at the end of class if we have time. But probably if we look it up, we won't understand it immediately. We would need some time.
There's YouTube for that. There's probably 6-hour videos.
So the formula we will be using is the integral of u dv. Notice these are separate letters, and there's a reason for that. You'll see that when we get to the example. So we're not integrating with two separate letters. It will all be x's really. But we label one as u and label one as dv. Just like with u substitution, we picked one to be u. This time we're picking one to be u and one to be dv. And this formula will equal uv minus the integral of v du. And that is something we should memorize, so this is something we should make a note card for.
Oh, I got you.
Woohoo!
Well, 2 of them. So I'll find. Wait, 2 of them? 3.
Not for long.
Thank you. No, I only need 1. Do better.
Okay, so let's look at an example, and I'll show you how we identify what u is and what dv is.
Just pointing out, the example has absolutely no numbers in it. It's all just letters.
That's where good math really begins. So basically, we're picking a piece of this function that we're going to differentiate, and we're going to pick a piece of this function that we're going to integrate. So on this particular function, I would pick x to be u. And there's a little way to remember, but just to show you what we're picking, I would pick x to be u, and I would pick everything else to be dv. It's kind of like product rule or chain rule where you're just identifying two different pieces. You're going to do some calculus to each different piece. With product and quotient rule, it was taking the derivative every time. This time it's a mixture. We're going to be taking the derivative of some of it and integrating some of it. So we picked u to be x, and we picked dv to be cosine x dx. So we're used to, with quotient and product rule, having u and v on the same level, but our original pieces that we're working with are actually kitty-cornered to each other this time. So the way we decide what u is we use something called LIPIT. LIPIT is just an acronym for the order you should pick your function. L stands for logarithm, log. I stands for inverse trig. I'm writing. P stands for polynomials. E stands for exponentials, and T stands for trig functions. And this is for u only. Once you identify u, everything else is dv. So if we had had a logarithm in this equation, integral of x, natural log x, we would pick u to be the logarithm.
What does P say?
Polynomials. So I just put poly.
Oh. Okay. I thought it was I.
So it's just the order you should pick u in. If there's a logarithm, you pick it first. If there's no logarithm, but there's an inverse trig function, that's what you should pick. If there's no logarithm, no inverse trig function, you should pick the polynomial. So on, so forth.
Oh.
And if there's multiple, you should check all these.
Yes. Well, like here we have exponential, sorry, here we have polynomial and trig. So usually it will consist of more than one, and we do pick the first one. So not necessarily the first as in x came first, the first in our list. Polynomial comes before trig. We pick our polynomial, which is x, to be our u. So now we derive u and we integrate dv. So we're taking the derivative of x. Here comes our first number.
Yay!
Or is that just lowercase l?
But we have to integrate dv. Now, we don't need to worry about the plus c at this point. We will worry about it at the very end. But we would just get a whole bunch of plus c's. We'd have plus c1, plus c2, plus c3. And eventually you just merge them all into one constant anyway. So we just save that step for the very end. So what is the integral of cosine?
Sorry.
Positive or negative? You're all so unsure.
Positive.
It's
Positive or negative?
It's negative.
It's positive. You guys are right. You just have no confidence.
Just kidding. It's positive.
So now we just plug it into the formula. The formula stated uv, so u times v minus the integral of v times u. So we just plug stuff in. What did we say u was? X. What did we say v was? Sin x. Minus the integral of v du, so we use sin x again. And then, I guess this is really 1 dx. Again, they probably won't dock the points if you don't write the dx, and you know after we multiply by 1 there should be a dx anyway. Just to show what we're integrating with respect to. So what conveniently happened for us in this second integral now? What's nice about it that wasn't nice about our first integral? Different about it.
You can integrate it.
I can integrate this with a formula now. I know the integral of sine. So this original one had a product including two variables. We had two sets of x's. We had x in front times cosine x. That was a problem. We don't know how to integrate that until we got this formula. This one only includes one x that we have to work with. So we can just integrate sine x now. What's the integral of sine x?
Negative cosine.
Negative cosine, but we were minusing, so
Positive.
negative negative makes positive. So sometimes we may have to repeat steps 1 through 3. Sometimes maybe we are left with a product of two variables again, and we'd have to take just this second piece
oh my goodness.
and do this whole steps 1 through 3 again. But in this case, we got an integral we could just integrate immediately. And then now we do not forget plus c. And next time we'll learn kind of an algorithm, a shortcut way to do it if it is. I mean, you could really repeat steps 1 through 3 over and over and over again. You could do it multiple times. Imagine if that had been x to the 10th. When we did it, our derivative would include x to the 9th. So we have to do it again until we only had a number left and not a variable. So we'd have to do it like 10 or 11 times. And we'll learn kind of a shortcut way next time. But this time, it's never gonna repeat more than once, maybe twice. We're not gonna be doing ones that repeat a lot. Did everyone get the steps down that wanted the steps, or should I pause for a second?
Pause for 2 seconds.
Okay. Happening.
Are actually more high than you would suspect.
Yeah, so we're in orchestra one day, and one of the girls plays the violin. She has glasses, and her violin's on her lap, and one of the lenses pops out and lands in the F hole. You know the little
Yeah.
holes, like they're that big on violins, and it lands inside. And Amber has Connor like hold it like this, and she has her baton and tweezers
And a pair of scissors. She's the
and a
person.
pair of scissors.
That's up.
got
She
it.
finally got it out. It was pretty crazy.
Okay, so you're gonna try this problem. This one you will have to repeat. So you are gonna have to do the integration by parts 2 times before you get an integral that you can integrate. And what type of function do we call e to the x so that we know where it goes in the limit?
No matter what we do, it's still e to the x.
So we had logarithms as first. Is e to the x a logarithm? No, it's the inverse of logarithms. We had inverse trig. Is this an inverse trig function?
No,
It's not a column.
It's not a polynomial.
it's
What about an exponential?
And then
And this is exactly what we mean by an exponential function. Exponential function is a number raised to a variable. And e is just a number. So I will pause the video and give you guys a few minutes to try this problem. Okay, so what would we choose for u on our first go around?
x squared.
Squared. Oh, gotta put stuff in the right order. So then what's dv? E to the x. We differentiate x squared to get 2x. We integrate e to the x with e to the x. It's not as important because the integral and the derivative are the same. But we are integrating to get b. We plug them into our formula. We have uv minus the integral of v du. And now we have to do it a second time. So what's u our second time? 2x, which would make du 2. And dv again is e to the x. So v again is e to the x. So this time again we're applying our formula. This time the minus sign will affect everything behind it. You can either do it automatically or you can write in parentheses. So we would have uv minus the integral of v du. And now we're finally to a point where we can integrate without doing parts. Remember, parts is because we have a multiplication problem. If we have 2 things multiplying together, then we need to do integration by parts. I shouldn't say 2 things, 2 variables multiplying together. If there's a coefficient out of front, then it wouldn't matter. And when we integrate again, we just get 2e to the x, but it should be plus because that negative sign distributes. That was mostly for Evelyn, so you're welcome, Evelyn. Okay. So let's look at another example. Most of what we've done so far, we've had to pick a polynomial to be u. Let's try one where we're not picking a polynomial as u. X ln 2x dx. So we have a polynomial and we have a logarithm. And according to Lippitt, which one of those two should we pick to be u? Ln of 2x, that whole thing, this time is u. Which would make dv x. So when we differentiate ln of 2x, what are we going to have to do to take the derivative of this? What rule must we apply? Chain rule. If it was ln of x, we know the derivative of ln x. Or we should, what's the derivative of ln x? 1 over x. But we have to do chain rule. So we need inside and outside. I'm going to write it underneath. Inside would be 2x. Outside would be ln u. Derivative of the inside is 2. Derivative of the outside is 1 over u. So we have derivative of the outside evaluated at the inside, 1 over 2x, times the derivative of the inside, so times 2, which does happen to come out as just 1 over x.
So you just took the derivative of
Yep,
Oh.
we had to do chain rule to do derivative of ln of 2x. I think that would be the case for any coefficient, so really we could change the formula. Instead of ln x is 1 over x, ln of ax is 1 over x.
So I was just thinking, I was like, wouldn't that work every time?
It would.
Yay. That makes me really happy.
Then I have to integrate my other side. I have to integrate dv. So what's the integral of x?
1 half x squared.
1/2 x squared. And now we put it all together in our formula. U times v. So ln of 2x times 1/2 x squared minus the integral of v du, the integral of 1/2 x squared times 1 over x. So this is why we choose logarithms instead of polynomials, because what's going to happen? What can we do before we integrate? It's x squared times 1 over x. Really was not a trick question. So really we just have minus 1/2 x dx. Is that something I can take the integral of without applying integration by parts? That's just an anti-power rule problem. So I'm going to rearrange. Usually we put the polynomial in front of the logarithm. So I'm going to rearrange so it's 1/2 x squared ln of 2x minus, and then we add 1, so we get x squared, and we divide by 2. What are we going to get if we divide by 2? 1/4. Plus c. So I want to do one more try problem.
So you add plus c after you're completely done.
Yeah. Otherwise, what would happen is we'd say originally plus C1, I guess. Really, it'd be plus C1 out front, and then plus C2, and C1 plus C2 is just C. It's just that all the coefficients you get at the end combine to be a coefficient. So we don't really care to call them separate coefficients.
So you just add c.
So I wanted to do this try problem. Actually, now that I'm reconsidering it, I thought, hey, we should do one where we have to rewrite it. but I think this might be an infinite loop problem that couldn't actually be solved with.
And you know that
Well, with polynomials, when you choose your polynomial, usually the polynomial disappears. When you take the derivative, you get 2x and 2, and you get a coefficient eventually. But with this polynomial, we have to rewrite it before we integrate. And this polynomial will not disappear. We could try it really quick, but I don't think it's gonna work. So let's try it. Let's just go through it really quick. Sign. You don't even have to copy it down if you don't want to, just to explore, see if it does work or not. Derivative here would be negative 2x to the negative 3. See, that's a problem. Our exponent here got bigger, kind of.
it got smaller, but
Got smaller, but it got bigger. And every time we took the derivative,
it just did.
it'd get bigger and it'd get bigger, and we'd be doing this forever.
So how do you solve?
There's some integrals we cannot solve by hand. We use computer algebra systems to solve it for us. So it could possibly be one we just can't solve by hand. I'm going to try the other direction though. Let's try sine x, and let's try x to the negative 2. And let's see if this works. So derivative of sine is cosine. Integral of this would be negative x to the negative 1. So we would get uv, so negative 1 over x times sine x minus v du, so plus, since we have a minus minus, 1 over x times sine x. Nope, yeah, sine x, right? Nope, du, not u. Sorry, cosine x. So then, let's try again. Eventually we're going to get a logarithm, and that's what I want to see what happens. U is cosine, dv is 1 over x, v would be natural log x, du would be negative sine x.
So the derivative of cosine is negative.
Yes, derivative of cosine is negative
The
sine x.
derivative of negative sine is negative cosine.
Yes.
So the integral of negative cosine would be negative sine. The integral of negative sine would be cosine. The integral of cosine would be sine.
I think so. You did that all really quickly, and I was writing at the same time, so I give no guarantees. V du. Again, we get a negative negative, so really plus.
That is really long.
So according to Lippitt, what should we pick when it's a natural log and a sine? Pick a natural log, which will take us, if we do the derivative of natural log, that's going to take us back in this direction. Okay, I think I see a way to solve it, but it's not something you would need for the AP test. But do you want to do it anyway?
Yeah.
Okay, so now I'm going to pick u as ln, dv is sine, du would be 1 over x, v would be, integral of sine is negative cosine.
Yours?
Yes. Yeah, I'm going to put
Just the loop of my
blah.
imagination.
It's all repeat. Plus uv, so plus ln x, negative cosine x. It is repeat, which is why I think we can solve it, because it does repeat. Minus the integral of v du, so plus cosine x times 1 over x. So then if I pick 1 over x is u, x to the negative 1, we would get negative x to the negative 2. Cosine x is sine. So we have everything we had before, because I'm running out of room, I'm just going to highlight it, plus uv, so sine x over x. Oh no, it's just going to cancel everything out. It is not going to do what I thought it would do. Because we'd get positive sine x over x, which would cancel out with our negative sine x over x. There is some times where you can kind of do a tricky way, where you end up with minus the integral of the same thing you started with. And then you add the two integrals together and just divide by 2. But that is not going to work out in this case. In this case, it's just going to all cancel each other out. So yeah, this is a bad try problem.
So if
It did not work.
cancels each other, if it cancels itself out, what happens?
Then we didn't solve it. We learned nothing. Which sometimes happens when you explore math. Sometimes it just doesn't work. That one just didn't work. So now I know for next year to change that try problem.
How do you know? Do you remember? Or do you
I say it. I look at them again next year.
go through all of your lectures?
Well, not like at the beginning of the year. Every week I look at all the lectures for the week and review and see if there's anything I need to change.
And
Or
from last year,
update,
you
or-
change it? Word salad.
Yeah.
Unless of course you change it wrong and then